Testing sound. Well, today we continue from where we were last time, in which I explain what the problem was and why the code last time was crashing and why it was so large. So first, here's the original code. I fixed this offline, but here's the original code. So this is basically implementing an operator equal for any two things of type AnyToken, which is a variant. And as a variant, it can be one of these several different things. And there's no like inheritance relationship or anything there. This is implemented using internally. It's probably implemented using placement new, and then there's a tag variable in there as well. And so, yeah, that's what's going on here. It's a tag, and then the tag, there's placement new, and no inheritance, no virtual functions, no nothing like that. And you can see what all these are. These are all pretty simple. Some of them have a value, which represents the value of the token. Sometimes the value is a string, sometimes it's an integer. Also, they do have inheritance, but the inheritance is from a base type. You notice that base type isn't even mentioned in here. And it's all because all of them have the original text. And there'll probably be other stuff added later. If ever I get to trying to make error handling better, I probably want to store the offsets, the byte offsets of where the original text came from in the file, maybe also the line number and stuff, and maybe even which file it's in, so that I can print out better error messages when I encounter tokens that somehow don't fit. So, yeah. What's wrong with this? Why is it? Well, first, how does it work? Right? Okay, so we're comparing any of these two things. The first thing we do is we check the tag. This is basically a way to check the variant tag, saying, is the variant tag equivalent to a tag that means that it was constructed in error and never really acquired a value? Basically, there was an exception somehow during the construction of the variant, and therefore the variant was constructed successfully, but somehow without a value. Which is a very weird situation, and I'm not sure exactly when it could happen. But I could see the possibility that maybe there is some kind of weird situation which it could happen. And if they're both like that, then we'll just call them equal. And if neither is like that, or if either of them is like that, but the other one isn't, then they're definitely not equal. Okay, so there's that. And that's pretty easy. But then we get to this thing, this visit thing. And what does visit do? First of all, the first argument to visit is a function, and we won't worry right now about this function, but that's what the first argument to visit is. The second argument to visit is, or the remaining arguments to visit, are the things that you're visiting. And visit can take 1, 2, 3 parameters. All of them will be variants. If it takes more than one parameter, what it will do is it will generate like the Cartesian product of all the possible things that could be for either variant. So, like you're passing in two any tokens, right? Because these are both any tokens. Well, either of the any tokens could be any one of these. So it will generate like kind of conditions, cases for the first one being an unsigned integer and the second one being an unsigned integer, or for the first one being an unsigned integer and the second one being an identifier, so on and so forth. The Cartesian product. So all of these ones and then all of those ones, and then this or first of all this one and all of those ones, then this one and all of those ones, and this one and all of those ones. So, the combination of any two possible types that the two variants could be holding, which is actually not quite right for what we're doing. Because I happen to know that all the cases in which the tags are different, in which the variants are holding different types, they're not equal. And so I don't even really need a special piece of code for those cases, which is the vast majority of cases. It's only a small number of cases, because how many are there? 1, 2, 3, 4, 5, 6, 7. So the Cartesian product is 49 functions, right? 49 different possible cases. And then, but only 7 of those cases are cases in which there's a possibility that it will return true. All the rest of them, all the other 42 cases, are ones in which it will also just plain out be false. And so that's it's a little bit silly to have this to do it this way. But so that's what visit does with two parameters. It generates cases for the Cartesian product of both parameters. And then what does this do? So this function, it takes autos, right? And in C++ 23, and I think 20, I think this was a feature added in 20, if you have a function parameter that is described as auto in the function signature, all that means it's a template parameter. And so we're basically saying this function takes two things. And it'll be either an unsigned integer and an unsigned integer, an unsigned integer identifier, or something like that. So it'll take two things, the things that are actually the real type stored inside the variant. And so that's what this does is, well, I want to know what those types are. So we basically say, well, in this template generation, T happens to be whatever this type happens to be. So we decay T, basically we remove all the references and constants and whatever. We say T is whatever the A is, whatever A is a reference to. And U is whatever B is a reference to. The type of whatever B is a reference to. And then we check if const expr. So this is a compile time if statement. And we're checking to see if these two types are equal. And when this template is expanded, it will be expanded with particular types for its arguments. And so then this will give a result for whatever, whenever you have two different types, it will give a result of whether they're the same type or not. And so when it has two different types for its argument, and then that's same, it actually is a const expression at template expansion time. And then I do another one. If const expression, so basically, if they're both the same type, then we check, is one of the two types that they're both the same, semicolon, then we just return true. Otherwise, we return A equals B. Well, notice how there's no equals for any of these. Now, you could trivially create an equal. You just, create the equals, make sure that the original text is equal and the value is equal, but the compiler doesn't automatically generate those equality operations. It could, and I thought maybe the spaceship operator additions that were made in C++, I think 20, did that. It would automatically generate for plain old data types like this, or things that were pretty close to being plain old data, that didn't have any constructors or destructors or whatever, that it might actually generate an operator equal. But it does not. And so what does this do? Well, it looks at these two things. How do I compare a keyword to a curly bracket? Or how do I compare a keyword to a whatever? Well, it can't do it, but it can compare to any tokens because it has this operator equal, right? And any token can be constructed with any of these things. You can basically give any token one of these and it'll construct it. And that's a single argument constructor, so that's a conversion operator. So there is, in fact, a implicit conversion from one of these types to an any token. You just construct the any token with the value of the type. So then it just does the any token equal, which is recursive. So it goes back here, it does this. That was the source of the segment fault. It was basically running out of stack space is what was happening. And so, yeah, ran out of stack space. So after this thing runs out of stack space, then of course you get your segment fault. And also too, if they're not the same type, then it returns false, so that's great. But otherwise, and it's generating all 49 of these options. And the thing when it's doing this is it has a table. Like the standard library, the implementation for standard visit in the standard library is if it takes 2 arguments, then it actually explicitly at compile time generates a table of little functions that are calls to this with the 2 arguments, right? Because it's a Cartesian product, right? It can't really generate an appropriate switch statement or anything. And so, like if you do that here, and we'll just slash star this and star slash this, and then we'll copy in this one here, back into here, and then, oh come on. Right, hopefully, there we go. Actually, what we're going to do here, under here, there's edit, code, uncomment. There is something to uncomment the code. We're going to find action. If you just repeat the operation of commenting with the line comment, it will undo that operation. Well, that's nice to know. So then we will just replace all of this here. There we go. And Explorer can compile away. We can come back here, undo what we just did. And it will take it a while to compile because, of course, it is generating all 49 of those options, which is what appears down here. That's what this big table is about. And if we look here, how many entries are there in this table? There's 1262 minus 12. So basically, there are 49 things in this table. So that is what this is. This is a table of all the different possibilities, right? And there's somewhere here there's a reference. There's this thing is there in here, and there's all these different ones, and most of them will end up being recursive calls, and it is really ugly. It is basically nearly impossible to go through this and figure out what's going on. All of these functions are basically generated at compile time. And there's a whole big bunch of functions in here. And then the pointers to these functions are stuffed into this table, which is what appears here. That's what's going on. So, what did I do to fix it? Well, first, no, this is the wrong way to do it. First, the insight is, we only really care about visiting one case, right? So one, if the A dot index is not equal to the B dot index, and this is basically an explicit, like, let's get the tag out. This is an operation that exists on variance, and it tells you the index of the type that's stored there. -1 is valueless by exception. This one will be 0, 1, 2, blah, 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 blah. But we won't. I don't want to rely on the index as actually referring to any specific thing, mostly. What I want to do here is I want to I actually do have something in this code that's different from what's in here, but I want to do the compiler explorer one first, because they're basically equivalent. There's just a few safeguards that are in this code that are not. I hope I left those safeguards in this code that are not in Compiler Explorer code. So first I check, are they the same type? If they're not the same type, then they're not equal. Then we check if one of them is valueless by exception, then they are equal. I could also have checked to find out whether they were whether they were the semicolon, but it doesn't really matter. So then once I do this, I know for A that they're the same type, right? So I just have visit to one of the two arguments. When I capture, use this capture syntax here to grab the other one, to grab the B. But the B is inside the lambda by capture, not by being passed in. And so standard visit is only getting one argument. When standard visit gets just one argument, it actually just uses a big switch statement for all the different possible, things that could be in the one variant type that you passed in. So then I say, okay, figure out what type it is that we're being, and this is still a template lambda. So figure out what type we were invoked with, like what is the type of a val here, since it could be anything. And then find out, decal type decay t decal type a val. Find out what type it actually is. And we go, okay, let's recover that type for that value out of B. So I basically go B val, do standard get out of T out of B. So here we make sure that B val, we get the same type out, and we know this will always succeed because this function is only called when A index equals B index, which means that T is the same as U would have been in this version over here, right? And so then we have this one if const expr here, but this if const expr is just checking, is the type the semicolon? Because the semicolon doesn't have a value. And so it's just the semicolon token. And so if it is the semicolon token, then we return true. Go, yep, it's the one we want. And if it's not the semicolon token, then we have to actually compare the value of the token. And then that's that. And so if we look at this function here, one, it's tiny, right? This is the function right here, right? And the reason why it's in foo is I basically just have this call right here, foo, right, where I call it just to force the function to be emitted because it's a template, it's an inline function, and so the compiler has no reason to put it in there unless you actually call it. And here it's it's inline, so it's basically inlined into foo. And if you look at this function here, it's really tiny, right? And you can kind of see what it's doing. It's comparing and checking whether they're the same or not, and if they are, then it does one thing, and if they're not, then it does the other thing, and it's a really simple, obvious function. And it's calling memcomp here, which is a little bit overkill for what it's doing, but what the heck. I think actually there might be something where it's checking, is this the identifier, and if it's the identifier, then it's using memcomp on the strings. And otherwise it's using, it's having a different equality. The spec is going on. I could go through this and make absolutely sure that that's what's going on, but that's what I suspect. And that's why it's comparing against, I think it's comparing against one a couple places here. I don't know. But, this is a very simple function. Much less complicated, much less code. And yeah, no exceptions were harmed in the making of this thing, because these exceptions are talked about here, but they're never actually thrown. Because it's impossible. The compiler realizes, if you turn up the optimization, the compiler realizes that it's impossible for this function to throw the bad variant access thing, because you already verified that the index was the same, right? So this is why this is what I did to fix the problem. And you notice now I'm doing a dot value equals b dot value, and these value types here do have an operator equal that works. They're basic types, like integers or strings or whatever, or enum values or whatever. So they're comparable. And even if they weren't comparable, they don't have there's no cast to the thing that they would be. They're just the thing that they're the thing that they are, and if they're not comparable, the compiler is going to toss an error because it can't convert them to something that is comparable. So this is all good here. This works, generates a tiny function. It's what I should have done in the first place. So what did I do here? There's some things here though that I kinda did I put in static asserts? I did not. Oh, there was an intermediate one where I hand unrolled this into a switch statement of my own. And that's where I had the static asserts because that mattered. Here it doesn't matter. I don't care about the static asserts because standard visit handles all of that, and this expansion. It all works. I might get an error if I create another token type that doesn't have a value, but that's okay. I should get an error because then I need to define an equality function for that one. I could do if const expr, here to figure out which equality function I should be using for the particular type. So it works. Before I had static asserts because I was actually testing the index value. Is the index value 0? Blah, blah, blah. Is it 1, 2? Well, I'm only checking 7 index values. If the number of things in the variant here, there's more than 7 items in the variant, then the code needs to be fixed. And so I had a static assert going, the variant must have only 7 things in it. If the variant has more than 7 things, this code is broken, and I had a little static assert about that and saying you need to fix the code. I had another static assert about semicolon being number 4, and again, a thing that you had to fix the code to make, to put in the proper index for a semicolon if semicolon wasn't number 4. Would have probably been a way to get the actual index for a semicolon in that code, but I opted instead to have the static assert going. This following code makes this assumption. If the assumption is broken, you need to fix it. But as I said, I'm not using the switch statement. I don't need to use the switch statement. The visit basically devolves into a switch statement all on its own, and the compiler then optimizes that switch statement away into something that's even simpler than a switch statement when it realizes that almost all the switch cases are the same. And yeah, it works. So that's what I did. The best thing about the standard visit case is it devolves into a giant switch statement, and the standard visit thing makes the switch statement exactly as long as it needs to be for the number of items. I don't need to have any of that stuff. So, yeah. Why did I do this? So now we get to this. So what I want to do here is I want to basically just have a data structure that contains all the any tokens. Right? I want to have an array of any tokens that I'm expecting the thing to match up with, so that's what I needed. So here. And then expected tokens. And I just put the list of expected tokens in here. And so here I can just say like that. And then I can say and is this right? Equal literal true. No, not Boolean literal true. Identifier. I think I can have SV here. What? There is a way for me to use SV. Okay, not in this file. Do I have it in this file? Yes, I do. One of the cases in which, in fact, you do want to use using namespace. So now we can go down here to this and say true SV and so is that the right thing to have here? Tokens. There we go. Now we can say T : operator : equal. First of all, we can use so this is what we want. T operator equal. This should be what we want here, actually. Except we want a ridge text, so we want like that. There we go. Right? We can construct a string with a string value. It should be able to do that. And then here we want a ridge text, ampersand, value, tokens operator, and, except we want bool and. And then here we want, again, but for this one we want false, false. And this is bool or, right? Yes. Okay. So one, let's find out what happens when I compile this, because it thinks that all of this SV stuff is oh, probably because it's const expr. If I changed it to not const expr, I bet it would work. Maybe, maybe not. No, can't be. So basically, trying to use string views here just doesn't work. I don't know why. Why can't you initialize a string with a string view? But apparently you cannot. That's kind of weird. But it's easily fixed. I just go around and remove all the SVs. And the result of this, of course, should have been false, because false and true are, in fact, 0. Oh, it doesn't matter. Not see here. So now there's a thing that you can use in these tests to, in fact, check an entire array to make sure that the entire array is equivalent. So now that I have these expected tokens, I actually could just null out a ridge text in all of them. But, and can I do this? Can I make it const expr if I do this? Wonder if it didn't like the trailing comma there. Python would be forgiving about that, but C++ probably is not. How about like that? Oh, well, it's missing some of them. So we've got x equals true, ampersand, false. Oh, we're missing semicolon. One, two, three, 4, 5, 6, 7, 8. This should have worked. What did it not like? This is a very long error message. Oh, it's not a constant expression. Well, okay then. I tried. It should be. All those are small strings. It should have realized, oh, small string optimization. Those are constant expressions. All right. Now, So now it's time to do because catch in fact has a way to do arrays. Okay. Writing tests. Yeah, this is basically this, that. So what we're looking for in here is we're looking for a way to do lists as a test case. And there very definitely is a way to do that. Matchers. Check that. Okay, that's the thing I'm looking for. I'm looking for matchers. And matchers have their own documentation. So we are looking for vector matchers. Equals. Huh. So let's see if this actually works. It might be that expected tokens has to be a vector. Yes, but what is a tokelisty? Okay, that worked. Now for the test. Does this actually... Indeed, it... What happens if I do this? I don't know what I need to do in order to be able to make sure that these are printed out. Because that would be the thing that we want here. So here in lecture test, I have a thing that, in fact, converts every token into a thing. And that's kind of what I need here. Is I need basically a thing that converts every token type into a string. But otherwise, this is a lot nicer code than this previous one. In fact, here, for example, if I just do this, like that, again, it will fail. Yep. Okay. If I do this, oh, that will fail to compile. That's not what I was looking for. There. That will fail to run. And this time it will fail because one of them is bigger than the other. But I think this is a lot easier to read than the previous one, than these. So that's good. All right then. Now, so this is going to run correctly, and okay, now we're going to look. What's the difference here? By the way, this is also streamed on a YouTube channel. All right. These are also live streamed to a YouTube channel. I'll put the YouTube channel in the chat and also on screen. And they're also live streamed to a Rumble channel. Just a bit. I'm trying to get the link to that. Let's see here. Well, that's kind of annoying. First of all, something isn't actually working about this. There we go. I'm going to make it work again. I'm maintaining my stream while you watch me, if anybody's actually watching. Let's try this one more time. All right. There we go. And the other place I'm streaming to is here. And I will print these out on the screen and So they're going out to two different places. That place and this place. Anyway, I just thought I'd mention that briefly. Not hugely important here. Oh, let's see here. There's one last thing I have to do. Then I'll start. Any questions? Real codingery? Why mess around with stuff and try to there. All right. Hello there, Sky the Dragon. He's joined from YouTube this time. So, anyway, I got this working. Now I'm going to, I'm in the process of checking in the change because it's a working change. I do have some more things I need to do with it. I don't yet. Oh, I added the keyword var, but I don't have any tests for it yet. That's not so great. Oh, we have somebody outside who thinks that they should play music really loudly. Hopefully you guys can't hear it because it's not very good music. So this is basically just about refactoring tests. So I am going to put in all the stuff that's in here about refactoring the tests. And IM says interactive. So this is interactive where I get to go through and make a decision about each possible change, each line. Yes, let's look. No, don't want to change. Okay, I didn't think so. Yes, we want to check here, check there. No. We want to look at this. Nope, don't care about that because we aren't adding that keyword yet. Nope, don't care about that because we're not adding that keyword yet. Yes, we do care about that because it's necessary for the operator equal to work. Nope, that's about the var keyword. There we go. So now this stuff is about the var keyword. And I'm going to have to add tests to the tokenizer to implement the var keyword to make sure that var, in fact, is a keyword. And to some extent, I don't care about while or any of these other ones that are being checked here. Here's what I'll do. Well, ask the AI. I've been asking the AI to do tests for me. And then we'll do this. Beam method. So we'll ask it to make this test, do this, and see what happens. This is agent mode. I don't know that I like the whole agent mode idea, but we'll see if this agent mode thing actually works for what I want to do here. Yep. And I don't like using the AI for this. One, I don't like agent mode because what I would prefer it do, if I'm going to try and have code at all, I want it to tell me what the code is, and then allow me to paste it in or do whatever it is I want to do with it. I don't like this agent where it tries to do all this stuff and compile it and all this other stuff. It's not what I want. But, here we are. Everybody else has decided they want agents, and so now we get agents. Now, the other aspect of this is that I don't want to use this to write any of the real code. I don't like using it to write the real code because I think it's AI typically writes pretty bad code. I'm willing to let it write the tests because the tests are basically very repetitive and templatized, and they can't make a whole lot of huge mistakes about the test. But for this, for when I actually implement this keyword and implement the scoping and all of that other stuff, I don't want to use the AI to do any of that. I don't trust it to do it. Also, too, part of this is me learning. I've never written a programming language before. And I know how to write a programming language, but I've never actually done it. And so, yeah. Let's see. It says it added the tests, but I don't see the... All right, we will run this command. I'm okay with you running this particular command. Let's see what happens. All right. Oh, it added 2 more assertions. Let's see. Okay. Well, let's look and find out what these differences were. Okay, these tests are acceptable to me. This looks good. What else do I want? I want one more test. White space, look ahead. So there. All right. Let's see if this does the right thing. All right, we'll run that. Let's see if that works. And we'll do a diff to find out what it actually did. I don't... and... Okay, it added 2 more assertions. Let's see here. So it did this. Made sure that vars was treated as an identifier. Yep, that all works correctly. Okay, good. Good. This is right. The one thing I don't like is the given a string with Boolean operators thing. Oh. There, it put in a lot of extra space there that I didn't want. And I also discovered a spelling mistake that I should fix. I should honestly fix this spelling mistake as it's not a spelling mistake. It's a grammar error. No. Yes. Yes. Done. Skip. Okay. What does the AI think this commit consists of? I am always curious. It's wrong. Because the var keyword no. There. This one, we're going to add a new line at the end of the file. Hey. uh, all right. Now we get to go into the parser and actually parse this whole thing out. So first of all, when we're parsing a statement, parse var will become one of the things that we could do. One of the things is assignment looks an awful lot like a var declaration. And it's possible we should, no, because var, we should have it introduced. Like, I already made the decision to not do what Python does and just sort of automatically create variables when you assign to them. So I want to treat a declaration and assignment as different. And then later on, maybe I can change it so that assignment is not a statement, but is instead an expression. I can change it to be like C++ is, or C. So since assignment is an expression, it has a value. It already actually does have a value in the way everything is implemented, so that won't be much of a change. But if I make it so that assignment creates variables, then I can't really do that anymore. So that's what I'm going to do. Now, it does look an awful lot like I hope that you are having fun, Sky the Dragon. Not C. It does look like it'll almost be exactly identical to assignment. How much of this scoping is going to be created? Like, I'm going to need to keep some data structures. So one of the things I'm going to have to do with this is there's a kind of a context data structure that's going to have to start going along with everything. But since this context data structure is going to have to go along with everything, maybe then that means that this parser needs to be an object instead, because it has some internal state associated with it. Because it's keeping not just the parse tree, which can be kind of constructed on the fly and returned as an answer, but it's also keeping a kind of a piece of meta information about the parse tree. Oh, this is going to be kind of confusing because I want to be able to catch uses of variables that you haven't declared. And also, I want to change it so that the identifier, like identifiers in the parse tree, contain a reference to the actual identifier that they are talking about in the static scoping. Which means I have to keep as part of the tree kind of what static scope is there is relevant at any given point. Okay. First thing to do is add, we'll add, not parse assignment, we'll add parse parse vardecal. And parse vardecal here. And here we'll do parse vardecal instead. Now, I could have use of a variable that you have not declared be a runtime error, in which case I could start keeping all the scope information at runtime. But I don't want to do that. I want to start keeping it at compile time. And I'm not sure how to go about doing that. This is a tricky problem to solve. Now, parse assignment. First of all, we are going to change it so that we, in fact, try to parse the var decal before we try and parse assignment. One of the reasons why is because variable declarations are easily tagged and rejected as being variable declarations right off the bat, because they have to start with the var keyword. And so you can easily check, does it start with the var keyword? If it's not, then we go, nope, it's not a variable declaration. Whereas assignment is more complicated, because it can start with an identifier. An identifier is a lot more, and you can actually have identifiers that are part of expressions. Like you can actually have a single identifier being an expression. It's identifier followed by a single, the assignment operator, the equal sign. And so this is a more complicated thing to parse, and all of these are really simple because you can just do look ahead 1 and find out. This one you actually have to kind of look ahead 2. And this is the catch-all. This one is very general and should match a lot of things. So now down here where we do parse assignment, we're going to do so first parse assignment parse, and it's going to be parse var decal instead. And this time we want here instead of something more like what while does. So so if it's a var decal, if it's a start is finished, then we're done here. Now if and we check here. So we look here, we're expecting a keyword, then we check, is the keyword var? Okay. Then we say so then we go to the next token, then we check. Yeah, I mean, in C++, they have to be cracked at compile time, partly because every identifier is resolved to sort of an instance of the identifier as a thing that exists within a scope. And so the identifier, once the compiler figures out what identifier you're talking about in any given spot, the identifier is kind of replaced with a reference to the kind of the slot the identifier lives in, which is related to the scope of the identifier. So here, if after ID equals finish, doing the short circuit. Yep. Now we're going to do the next thing here. Oh. I have to do this differently because I want to. So I'm going to have to do this semicolon, not ID. There, like this. And then I can go there. Now I can do this, except that's what we'll do. It's a little bit ugly, but it still works because we actually care about it after this, and it will just automatically disappear when we do the return. All right. Then here we check if no and I don't care about after ID because I don't. Yeah, I can just do start here. I can just do start like I did all these other times. And then I can do start here. And then turn parse result. And we can go here. No, we don't care about current parent. Yep. Like this. . Yep, like that. So basically we need to have it be an operator equal. If it's not, then something's wrong. But we don't actually care about what it is. We just care that, like, once we know that it's an operator equal, we're good and we can move on to the next token. Now what we want here is we want to do and here we want start, not after equal. And if there was an expression, here we'll be a little bit more complicated with our logic. I'm okay with this. If remainder not equal to finish, and then here we go again. We just say like that. Otherwise, once we get down here, we know that we have a valid expression, and we can return and this is all good. Or what I could do here is if I could do this, if not expr, and like that. Like that. Like that. All right. And here we would want a var decal. And this. Now, this is not really what we want exactly, but it's close to what we want. The parser part should be done, and I want to test to make sure that it actually compiles. But there's a major refactoring that needs to be done here. Okay, so does this compile? Oh, well, yes. No symbol name type. Oh, it is complaining that I know what it's complaining about here. It is complaining that I don't have anything here for any of these simple evaluator things or whatever. So we're going to put these in here, and we're going to make them not do anything. Sure. Let's do that for this. And here, like that. That's probably about right. And then this would be making this work for the prefix stringizer is going to be really interesting. I'm just going to punt and put this here, and it'll be wrong, and then I'll fix it later. And also, this is wrong, because I need to do... Yep, like that. And down here, this is entirely the wrong thing to do here, but I want it to compile, so we'll put it in. Oh, that's because here in parser.hpp, I have to AST node. Oh, I see. Oh. Yeah. There. Oh, this actually has to do something. Let's see, how does assignment work? Oh, assignment is implemented down here. Vardecal. So I punted on a lot of things just to get stuff to compile. Most notably, I punted on actually managing static scope. But now variable declarations do, in fact, compile, this part of the grammar is technically now implemented. But it does not do what it is supposed to do. And figuring out how to make it do what it is supposed to do is going to be a very interesting task. So var decals, when they're seen, should devolve into assignment statements on execution. So it doing in this part here, in this simple evaluator, it doing something that's approximately this is in fact the right thing to do. Well, I'm glad that you're doing the thing that you're supposed to do, Sky. But I'm not sure what that is. Are you a variable declaration? So at runtime, this is approximately what it should be doing. The thing is it shouldn't really be doing this, because this just creates the entry in the table out of nowhere. And so it should, in fact, be just putting the value in the table, but the value should exist. The table should already have the identifier in it at the point that it gets to this spot to evaluate it. All right. Here is what we are going to do. In statement list, one of the things that we might do as part of statement list here is create a stack frame. Which means that statement list needs, as part of its thing, because variables are going to be associated with blocks. And so statement lists are thing for holding a block, a set of statements. And so what are the things that might be associated with this? Will be a Indeed, that's exactly it. So every statement list might have a set of identifiers associated with it. So then the simple evaluator will have a set of activation records. So the simple evaluator will have a bunch of things in it called activation records. Yes. And then we're going to have yes. Stack. All right. So then, inside the simple evaluator, when we start a statement list, is if. And then what we're going to do here actually we're going to have no. Statement list, : stack frame _t There we go. So this is a type, right? I declared a type in here. It's called stack frame t. There is a stack frame t that's in statement list. I don't understand what you're complaining about here. And then here, we'll go like that. Like that. Okay. Now what we can do here is stack sub 0 and what does this return? Yes. There. Like that. It is ugly as sin, but it works. Okay, now let's see here. Oh, well, yes, it is not. There. That's better. And then we can just refer to identifiers .size here and identifiers here. There, like that. All right. And then here, now we do here stack underscore dot back dot find All right. And then here, aha. Well, there. Okay, now this is still broken because this will break all of the tests. It'll break all of the tests. Well, not all of the tests. Any test that uses an identifier, it will break for a lot of different reasons. Partly, there'll never be a current frame because nobody ever sets the list of identifiers in a frame anywhere. But this does all compile. And I kind of want to end for the day. I've done this for a couple hours. I'm good. I'm going to finish for the day. And then we'll pick it up next time, which might be not be until Monday the 3rd of November. Monday the Monday the 3rd of November will probably be the next time I stream, because I have a work trip to do for my day job, and that work trip is going to occupy all of next week. I will be on the East Coast. I currently live in Seattle, and I don't really have a streaming set up for my laptop that I'll be bringing with me, and so even if I wanted to, I couldn't, and I'm going to be like, everything's all going to be discombobulated. There's probably no way I'm going to be able to find time to stream, even if I did have a streaming setup that worked. But this is sort of a preliminary thing that's almost what we want. Calling these stack frames is a way to do this. The other name that is used for these kinds of records in programming languages is activation records. And this actually, I probably should call it an activation record, because stack frame refers to a specific implementation of activation records, which is approximately the implementation I'm using here. But there are other ways to implement activation records. And you might want to use them for things like coroutines. When you have coroutines, you need activation records to stick around even after the function has apparently quit executing, because the function coroutines have functions that can basically pause themselves and say, okay, you can go do something else, which means that the activation record for that function needs to stick around for when that function comes back to life again. And continues executing. And so in there, your activation records, in fact, look more like a tree and instead of a stack. And that is the reason why the term activation record is used instead of stack frame, because stack frame is not necessarily implies a particular implementation for your activation records that may not, in fact, be true in all cases. And so you want to use a more abstract term to refer to what you're talking about. But I will leave stack frame in here partly because I'm actually implementing these as stack frames. This programming language doesn't have coroutines, and therefore implementing your activation records as a plain old stack is perfectly acceptable. All right, I will wish you all a fantastic rest of your day, and I should be back, as I said, on the 3rd of November.